Hello, everyone. Welcome to the last session of online mini course about sub-intuitionistic logics. Today we're going to talk about the sub-intuitionistic logics, and the outline will be as follows. First, I will discuss our work on sub-intuitionistic logics by considering neighborhood semantics. In last session, we discussed about sub-intuitionistic logics with Kripke semantics, but today we're going to talk about sub-intuitionistic logics that Kripke semantics cannot be theoretic for them, so we need to construct the new neighborhood semantics for them. We discussed logic, completeness, conservativity result with respect to IPC, two different types of neighborhood frames. So, what is a sub-intuitionistic logic with neighborhood semantics? Dick DeYoung and Shi Mohammadzadeh Maleki in 2016 have introduced a logical system WF bigger than F and two forms of neighborhood semantics for them. For more information about these sub-intuitionistic logics, you can refer to two papers of them, this and this one. Also, there are other papers, but these two papers are very useful. First, I would like to introduce n-neighborhood models. We first introduced a type of models like the ones for modal logic. Consider the frame F, the triple WGN. Remember that in the neighborhood semantics for modal logics, we also had the W and neighborhood, N. But here we just add the G that I will explain why we did it. This is an n-neighborhood frame of sub-intuitionistic logics if n is a function from W into power set W such that has these two conditions. Case 1 says that for all W in the W, for the every word in W, the set W should be in neighborhood of W. And the case 2 says that neighborhood of G just is the W, the set W. In this case, we say that G is omniscience. Of course, n-neighborhood models are defined from phrase in the usual way with the clause, this. A then B is true in W if and only if complement of AM union BM be in neighborhood of W. For other conjunction, disjunction, and also other connectives, truths defined as usual. In analog to Kripke frames, we call frames with omniscience elements rooted frames. The existence of omniscience elements lead to the important fact, lead to prove this theorem. If M is rooted, then A then B is true in M if and only if AM is under BM. Remember that AM was the set of words that in that word A was true. This is essential to prove soundness for the rooted models. This theorem is essential. But we were able to prove that omniscience elements can always be added to a model without changing the truth values in the existence world. So in this way, we get soundness for all models. Similar this also we had for the sub-intuitionistic logics with Kripke semantics, for sub-intuition logic for F and other logics between IPC and F. WF is the logic given by the following axioms and rules. These axioms and these rules. The rule 6 is called the Forcioli rule or weakening rule, introduced by Corsi, and the rule 14 is analogous to this rule that we called it RE in the modal logic, in classical modal logic. I wrote these three rules with another color because the logic WF meets the following axioms of F. If you remember, in the logic F, these axioms are true. But here, instead of these axioms, we just have the rule of them. I mean, for example, here, A then B, B then C, A then C. These have been replaced in WF by the 3 rules 10 till 12. Typical for intuitionistic logic is that axioms and their corresponding rules are different in strengths. As you can see here, and we will be seeing in the future. But about the completeness. Can we prove completeness of this logic by n-neighborhood semantics and by canonical model or not? My answer is no, because we were unable to prove completeness of WF with respect to n-neighborhood models. The problem is that complement of X union Y is equal to complement of Z union W is possible without X be equal to Z and Y be equal to W by the definition of truths that we had for the A implication B. But we need to have to separate them. I mean, separate X from Z and also Y from W in order to prove completeness. That was unfortunate because n-neighborhood models do well with respect to translations to modal logic as the models are the same. Anyway, we introduced a second type of models and we call them NB models. That in the future I will introduce them. But what is the NB neighborhood models? Instead of n, we just write here nb because of the binary. WJNB is an NB neighborhood frame if NB is a function from W into power set W to power 2 such that has these two conditions. First, for all word in W and for all xy in power set W, if x be under y, then the pairs x and y should be in the neighborhood of W. And the second condition says that neighborhood of G just is the set of pairs xy such that x be under y. This is the classical true implication. And also not that x is under y if and only if complement of x union y equal to W. I write this because recall that in the neighborhood, n-neighborhood frames for we define truths for NBAG. In that case, energy was exactly the set W. But here, this sets, and we know that this is equivalent to this set. Here also G is called omniscient. Similarly as before, it is expedient, but we could do without. Valuation V from atomic to power set W makes M, models M, an NB neighborhood model with the clause A then B is true in W if and only if the pair A and B in neighborhood of W. And otherwise the standard definition of truth and validity. Also, for the proof of soundness and completeness, we need to define some concepts. For example, validity on a frame. A formula A is valid on a frame F if and only if A is true in every model based on that frame. And a rule like this, A1 till A and B, is valid on a frame F, and we write like this, if for all M on F such that M models A1 till M, also M models B. Then we could prove this theorem. This theorem says that A then B is is true in M if and only if AM be under BM. Of course, I'm going to prove this. This is not hard, but What does this mean? This means that, first from left to right, this means that for all world in models, or for all world in W, A then B is true. And this means that for all world in W or in M, it's not, there's no any difference between them. And by definition of truth, the pair AM, BM be in NBW. But here we know that G is also in W, and also we know that NBG is exactly the pair XY such that X is under Y. What does this mean? This means that, and from another side we know that AM, BM is in NBG by this. So we conclude that by this and by this, AM is under BM. Another direction is also, these all of them are equivalent. And also we have this from case 1, we can conclude the second one. Completeness can be proved by canonical models as usual. So we need to define some concepts, for example, theory. What is the theory? What is the neighborhood in our canonical models, and something like this. First, we define the concept of theory here. A set of sentence delta is a theory if and only if A be in delta, then conjunction of them also be in delta. If A then be probable, then if A in delta, then B should be in delta. If we have A probable, then A should be in delta. This is the definition of theory. And also we define A is F sorry, I should write here WF, not F. This is my mistake. Gamma, A is WF probable in gamma, is defined as this. A is derivable from gamma using the rules 6, 10, these rules, when there are no assumptions, and the rules 5, I mean modus ponens, only when the derivation of A then B contains no assumption. Come back to the WF. This, it says that when we have it says that for these rules, these and also 12 and 14, we shouldn't have the assumption. This means that, for example, if gamma proof A, then we cannot conclude. Then or for example, if gamma proof, then we cannot conclude that, and also gamma proof. We can see. Then we cannot conclude that gamma proof A, then we don't have something like this, just in case that example A, then we can conclude B, then A without assumption. But also above the modus ponens, just from A then B, we can conclude B, just in case that A then B prove without any assumption. That we call this weak modus ponens, similar to the proof for completeness for the W, and also similar to the definition of definition of logic F. So this definition is very important. And also gamma, A is valid in gamma is defined as for all M and for all W in M. If MW force gamma, then MW also force A. Then we can prove that delta is a theory if and only if delta proof A, if and only if A is in delta. As before, from left to right side is easy, and also from this to this. And for the proof of this direction to this direction, we just use induction on the complexity of derivation. You can see the proof of these in the papers, all of them. But here also we need a weak deduction theorem. We don't have full deduction theorem. I mean, we have this. A proof B if and only if A then B be provable. Similar to the reasons that we gave you in the logic F. Then we can conclude this. Corollary. A1 till A proof B if and only if conjunction of them, then B be provable, and also this. Then we define a set of sentence delta is prime if and only if A or B in delta, then A be in delta or B should be in delta. This is the definition of prime. Finally, we could prove that if sigma doesn't prove D, then there is a prime theory delta such that delta contains sigma and D is not in delta. Again, for the proof of this theorem, we need to define a set such that has these conditions. By assumption and by definition of probability, we conclude that D is not in sigma, because if D will be in sigma, then we shouldn't have this. Enumerate all formulas with infinitely many repetitions, B0, Bn, and define delta 0 is equal to sigma, delta n plus 1 equal to delta n union Bn. In such case that delta n Bn doesn't prove D, otherwise delta n plus 1 should be delta n, equal to delta n. Then if we take delta to be the union of all delta n, this delta has these conditions. You can check these. By that theorem, I mean by this theorem, we could prove this lemma. Before this lemma, it would be better to define this. Let WF be the set of all prime theorized. Given a formula A, we define this set as follows. Is the set of all theorized such that delta is in delta WF and A is in delta. The set of all prime theorized that has these conditions. Then we could prove that if C and D are formulas, then we have these cases. The proof of A, B is immediately, but I'm going just to prove the case 3 from left to right. Right to left, sorry. Because the other direction is obvious. This lemma is very important for us to prove completeness. I proved this by contraction, so I assume that C, then this is not provable. Then by the weak deduction theorem, I conclude that C does not prove D. Then we just need to define the set sigma, say C, then sigma the set C, we assume that, and D is the set D exactly. Then there is a prime theory delta such that delta, then there is a prime theory delta. There exists a prime theory like gamma such that gamma C is in gamma, but this means that B is not in D. So we could prove this direction by using this theorem. Now we are ready to define canonical model. Canonical model defined as usual the set of all words that is the set of prime theories G, N, B, W, F, and V. G is the set of theorems of W, F. And for each gamma in W and all formulae A and B, we define neighborhood of gamma as this. The set pairs A, B such that A then B is in gamma. And if P in atomic, then valuation of P defined this set. I mean the set of gamma such that gamma in WF, WWF, and P is in gamma. Now I claim that W have the disjunction property, and therefore, of course, we proved it by the way of the IPC, I mean subintuitionistic logic, and by the slash that I didn't mention it here. So W is a prime theory, and also it is easy to see that in the canonical model, in this model, W is the omniscient. Why? I think it would be better to write it. I'm going to show that what does this mean? I need to show that is this is the meaning of omniscience word. But by the definition of canonical model, we know that this is equal to this pair A or B such that A then B, B in WF. But this means that A then B is probable, and now by the previous lemma, I mean this lemma, we conclude that the set A is under the set B. So this is equal to, so we conclude that, finally we conclude that NBWF is the set of A, B such that A is under B. So we prove our claim, I mean we prove that in the canonical model W is if F is the omniscient. Also, for all gamma in W, if A be under B, then the pair AB is in neighborhood of W gamma. Why? Because if AB is under B, then by the previous lemma again we have this, and so A then B should be in gamma, because in the definition of theory we had this condition: if this, then we should have this, and we know that gamma is the theory, prime theory. So we define the canonical model for WF. Now, in order to prove the final theorem, we need to have also this lemma. With n neighborhood model, we couldn't prove something like this due to the problem that I said in the previous slides. If NAB from W to power set W to power 2 is a function such that for all gamma in WF, and be a gamma be in the set pairs AB such that A then B in gamma, then AB in NB a gamma implies A then B is in gamma. We should conclude from this case. And this proof of this lemma is also easy. You can see the proof of this in the papers. Then, and finally, we could prove that through lemma. I mean, for every formula A, if MWF is the canonical model of WF, then this set is equal to this. This means that for all W, if EB, for all words in WF, if EB true, then it should be also in the set gamma, for example, gamma. The proof is also by induction on E. So we can show that WF is sound and strongly complete with respect to the NB neighborhood frames. Soundness is straightforward. We just need to check that whether the axioms and also rules of WF is true or not, and this is very easy. But for the other directions, we assume that first we assume that sigma doesn't prove A, then there is a prime theory delta contains sigma such that A is in delta. We proved this theorem before. So in the canonical model, we have this delta valid sigma, and also delta A is not true. This means that A sigma doesn't valid A. A is not valid in sigma. So prove completeness for weak F or WF. Sometimes we can call it WF or weak F. But what is the difference between N validity and NB validity? As you saw, we couldn't prove completeness for WF with N neighborhood semantics, but we could prove completeness for WF with NB neighborhood semantics. The question is that are N validity and NB validity the same or not? My answer is that they are not equivalent. There is no. My answer is no. Because if we consider these two axioms that I named them A and B, these very obvious axioms, A then B if and only if A or B then B, and A then B if and only if A then A and B. These two axioms are valid in N neighborhood frames because of the definition of truth in N frames. The proof relies on the fact that this set is equal to this set, and also this set is equal to this set. But these two axioms in NB neighborhood frames are not valid true. I mean, WF doesn't prove this, and also the logic WF doesn't prove this. So, an additional rule was find which is valid on N neighborhood models, but not on NB neighborhood models. So we add this rule to the system WF, and we called it WFN. I mean, WF plus this rule, we can conclude WFN. Since this rule is important and very long, it would be better to keep it and write it here. We call this the rule N. A rule like N is valid on a frame F if on each M on which the premises of the rule are valid, the conclusion is valid as well. Then we could prove this theorem. M models A then B if and only if AM is under BM. Again, this crucial lemma relies on the existence of ambiscience element. You can also prove this yourself, or you can find this proof of this in the papers. But I'm going to first prove the soundness. Of course, for soundness, we just need to check that whether this N rule that I wrote, I mean this N rule, is valid in N neighbor frames or not. We just need to check it because others we checked before. In order to prove it, I assume that M models C then A or D. M models C then A or D, and also I assume that M models A and C and B then D. I call this the condition 1, call this the condition 2, and also these two, I mean, I should consider that M models A then B or C, and M models A and C and D then B. I don't need, I will not concentrate on this because the proofs are similar. I just consider these two conditions. And then from two conditions, I mean M models this, I will prove that M models A then B, then C then D. And if we consider this, then we will be able to show that M models C then D, then A then B. So, assume M models C then A or D. What does this mean by definition of truth in N models? This means that CM is, and also by this theorem, this means that CM is under AM union DM. And this means that AM intersection CM intersection BM is under DM. From this and this, I'm going to prove that complement of AM union BM is under complement of CM union DM. If we could prove this, then the proof will be complete, because by the definition of truth in N models, if we have this, then, and by this, then implications of this, then this will be true in models. So I'm going to prove this. Let W is in complement of AM union BM. What does this mean? This means that W in complement of AM or W in AM and W in BM. If W in AM, we distinguish W in DM and W in complement of DM, because anyway W is in or W is in the set. Now, if W be in this set, DM, we are done because W will be in this set. If W is complement of DM, then from 1 we conclude that W in complement of CM. Also done, because we have this. But if W in AM and W in BM, we distinguish again W in CM, complement of CM, and W in CM. Now, if W in CM, complement of CM, we are done. If W in CM, from 2, we conclude that W in DM. Also done. So we could prove that this is under this. So from the previous theorem, we conclude that M models A then B, then C, then D. So we prove soundness. But about completeness. Also, completeness of WFN proves similar to the before case. I mean by canonical models, and also by proving some other theorems that I didn't mention, explain them. You can find the proof of all of them in our papers. But there is a one-to-one correspondence between NB models and with some conditions and N models. What is that conditions? There is one-to-one correspondence between N frames and NB frames close under the equivalences. What is the equivalences? This means that if XY in neighborhood of W, NBW, and complement of Z union W is equal to complement of the X union Y, then ZW should be in neighborhood of W. This is the definition of equivalences. So, for every N frames, there are NB frames close under the equivalence, and also for every NB frames that is close under equivalence, there is a N frames. There are a correspondence between them. So herefore, we can do without N frames. So we can prove theorem like this. The logic WFN is sound and strongly complete with respect to the class of NB neighborhood frames that are close under equivalence relation. But the other logics between WF and F, I'm going to introduce other logics that are weaker than F but are stronger than WF by neighborhood semantics, because Kripke semantics cannot be treated with these logics, so we need to construct neighborhood semantics. The other logics between W and F by dropping axioms like CDI, recall that CDI are the axioms that WF, in WF these are not true, but just the rules of these axioms are true in WF. We have also in between rules, between WF and adding the rule I, axiom I, these two rules that we call them R or IL, sometimes IL. These two rules. Sorry, what time do you have? 40 minutes. 40 minutes? Okay. Moment to see whether, so I think it would be better to have a break for 14 minutes and then we'll come back after 40 minutes. Okay, let's go ahead. And some properties of frames and characterizations similar to this we had also in the Kripke semantics. F is closed under, we say that F is closed under intersection if and only for all W in W, if these two pairs XY and XZ be in neighborhood of W, then X and the pair X, Y intersection Z should be in neighborhood of W. We call this intersection. And F is closed under union if we had this condition, XY is if XY in neighborhood of W, ZY in neighborhood of W, then X union Z, Y should also be in neighborhood of W. And this condition called transitivity, if XY and YZ be in neighborhood of W, then XZ should also be in neighborhood of W. And also the condition upset says that if XY in neighborhood of W and YB is under the Z, then the pair XZ also should be in the neighborhood of W. And the definition of downset says that XY in neighborhood of W, and if Z being under X, then the pair ZY should be in neighborhood of W. And F is closed under superset equivalence if and only if for all W in W, if XY in neighborhood of W and complement of X union Y be under the complement of X prime union Y prime, then X prime Y prime should also be in neighborhood of W. We define this and then we could prove this lemma. This formula that we call this C characterize the class of NB neighborhood frames satisfying closure under intersection. This formula that we called it the D characterize the class of NB frames satisfying closure under union. And also this formula that we called it I characterize the class of NB frames satisfying transitivity. But I'm going just to prove the case 1. The proof of other cases are similar, and also you can find the proof of them in our papers. So first, I'm going to prove that if our frame satisfying closure under intersection, then this formula should be true in all models on this frame. Let F be closed under intersection and M be any model based on F. We need to prove that for all W, this pair, I mean P then Q and P then R, M, P then Q and R then M should be in neighborhood of W. Because if we could prove this, then by definition of truth, it's obvious that W valid P then Q and P then R, then P then Q and R formulas. In order to prove this, it's sufficient to show that this is under this. Why? Because we know that in the NB neighborhood frames, if X be under Y, then always the pair XY should be in the neighborhood of W. So if we could prove this, then we conclude this case. So assume that W is in this set. This means that W, P then Q is valid in W, true in W, and also P then R true in W. Then what does this mean? This means that the pair VP and VQ in neighborhood of W, and this means that by definition of truth, VP and VR, this pair is also a neighborhood of W. But additionally, we know that frame is closed under intersection. What does this mean? This means that if XY be in a neighborhood of W and if XZ be in neighborhood of W, then the pair X, Y intersection Z should be in the neighborhood of W. So by these two conditions, we should conclude that VP and the intersection of these two sets, I mean this pair, should be in the neighborhood of W. This means that in W, P then Q and R is true. Hence, we conclude that for all W, this is a neighborhood of W. We conclude from this that if W be in this set, then it also is in this set. So this pair is in the neighborhood of W. So our proof for this section is completed. But for another section, for another direction, I mean, again we use contraposition. I mean, we suppose that the class is not closed under intersection. So there is a frame F and also world in F such that this pair XY neighborhood of W and XZ neighborhood of W, but the intersection of these, I mean XY intersection Z, is not in neighborhood of W. Consider the evaluation V such that has these conditions. I mean, VAP, we assume that VAP is the set X, VR, valuation of R is the set Z, and valuation of Q is the set Y. Then, by this assumption, the pair VP, VQ will be in neighborhood of W because we had this. So, from this and by the definition of truth, we conclude that P then Q is true in W. Again, VP, VR is a neighborhood of W by this condition and by this assumption. So we conclude that P then R is true in W. But we conclude that VP, VQ and R is not in neighborhood of W because we assume X, Y intersection Z is not in neighborhood of W. And X is equal to this and Y intersection Z is equal to this. So we conclude that P then Q and R is not true in W. So this set is not in under this set. So by definition of neighborhood frames, we conclude that in the omniscience world, this formula is not true because the neighborhood of G was exactly the sets that was exactly this pairs that something like xy such that x is under y. But here, since this is not under this, so we conclude that this formula is not true in G. Therefore, in this frame, this is not true. So we could prove two direction of this case. Okay. But now about the characterization of rules. This is a little bit different from the previous, the proof of this is a little different from the proof of the previous lemma. Now, the rule, this rule, P then Q, Q then R, then P then R, characterize the class of NB frames satisfying closure under down set. This rule characterizes the class of NB frames satisfying closure under upset. And this rule characterizes the class of NB frames satisfying closure under superset equivalence. Again, I just prove the case 1 and the proof of other cases. For the proof of other cases, you can refer to our papers. Again, I assume that the frame is closed under down set. And in order to prove that, to show that this rule is true, I need to assume that M models P then Q. Okay, for all M on a frame F, M models P then Q. This part is exactly the proof of similar to the proof of the previous one. So we have to prove that for all M on F, M models this. The conclusion. Okay. For this purpose, we show that for all M on F, this is under this because if you remember, we proved that if M models A then B, then AM is on, if and only if AM is under BM. So if we could prove this, then we can conclude this. For this, we assume that W is in M and W valid Q then R. Then this means that the pair VQ and VR is neighborhood of W. Also, by assumption, we know that VP is under VQ. Okay. Then, because we had this, we assume that M valid P then Q, and by the theorem by the lemma that we proved, VP is under VQ. Yes. So we know that the frame is closed under downset. So we conclude VP VR is neighborhood of W. Therefore, we conclude W valid P then R. So this set is under this set, i.e. this means that for all M on F, M models Q then R, then P then R. Okay. But for the other direction, again we use contraposition. Suppose that the class is not closed under downset. That is, there is a frame F and world in F such that XY in neighborhood of W, Z is under X, but ZY is not in neighborhood of W. Since we know that P and Q, then Q is true in our system, in our WF is probable, and hence valid on F. Okay, it's sufficient to falsify Q then R, then P and Q then R. Because, like this, P and Q then Q, then Q then R, and P then and Q then R. Awesome. Okay. It's sufficient to falsify this on the frame. Now consider the evaluation V such that VP is equal to Z, VR is equal to Y, and VQ is equal to X. Then, by this assumption, VP and Q is VP, and also by this. And it's equal to Z. So, we conclude VQ, VR in neighborhood of W because of this. And also, we conclude that VP and QVR is not in a neighborhood of W because of this, and consequently we conclude that by this that Q then R is true in W, and P and Q then R is not valid in W. Hence we conclude that this set is not under this set, and so in this model Q then R then P and Q then R is not true. So the proof complete. Now I wrote these axioms and these rules with their names. These axioms called C, these axioms D, I, IL, IR, and N2. These are important for our work. Then we could prove the completeness of these logics. I mean, if we add these axioms and rules to WF, then we will be able to get new logics that are stronger than WF but are weaker than F, and sound and complete, and are sound and complete with respect to the special class of neighborhood frames that I will explain in the future. We could show that if WFC, I mean WF plus C, is under L, then the canonical model of logic L is closed under intersection, and WFD is sound and complete with respect to the class of neighborhood frames that are closed under union. WFI is sound and complete with respect to the class of neighborhood frames that are satisfy transitivity. WFI is sound and complete with respect to the class of neighborhood frames that close under upset. WFIR sound and complete with respect to the class of neighborhood frames that close under downset. And in the last, WFN2 is sound and complete with respect to the class of superset equivalence neighborhood frames. Again, I just proved the case 1. Other cases also, for the proof of other cases also, you can refer to the papers. So now I'm going to show that if L contains WFC, then the canonical model of logic L is closed under the intersection. So suppose that in the canonical model of logic L, Y be neighborhood of gamma, and Xz also be neighborhood of gamma. By definition of NB in the canonical model, there exists formula A, B, and C such that XY is equal to this, and Xz equal to AC, this pair. We explain all of them in the canonical model, where A then B is in gamma, and A then C is in gamma. Hence, we conclude that conjunction of these also in gamma. And from the other side, we know that, and by using the axiom C, we know that A then B and A then C, then A then B and C is in our logics. So, we know that in the definition of theory. Now we have this. Is true in WFC because this is axiom C, and we know that A then B and A then C is in gamma, and finally by definition of theory, we know gamma is theory. We conclude that A then B and C also is in gamma. Hence, we conclude that A, B, and C is neighborhood of gamma by the definition of a neighborhood in canonical models. Therefore, since B intersection C is equal to B and C, we proved this before, and we showed this in the previous, in the before slides. B and C, we conclude that X, Y intersection Z in neighborhood of W, so NB is closed under intersection. Okay. So generally, I'm going to say this theorem. If gamma be under this set C, D, I, L, I, R, and 2, we will write WF gamma for the logic obtained from WF by adding to WF the schemes in gamma as new axioms and rules. Then we can say that if we can prove that if gamma is under this set, then WF gamma is sound and strongly complete with respect to the class of neighborhood frames with all the properties defined by the schemes in gamma. This theorem proved by this lemma, and this is obvious. Okay, but now all of these logic that till now I've introduced in this session are weaker than F, because in those logics we don't the axioms, in some of them C is not true, in some of them D is not true, in some of them I is not true. I mean the axiom of C, D, I. And we know that the logic F is the smallest set of formulas closed under instances of WF, C, D, and I. So F is sound and complete with respect to NB neighborhood models closed under intersection by this, union by this, and satisfying transitivity by I, axiom I. So last session we proved that F is sound and complete with respect to the Kripke semantics that has no relation, that has no condition on their relation. And now we proved that F is sound and complete with respect to the neighborhood models that close under intersection, union, and satisfying transitivity. Here we also introduce two of other axioms that we call them C hat, D hat. And we will show that these axioms will turn out to be equivalent to the rules I, L, and IR respectively. I mean, C hat is equal to IL and D hat is equal to the rule IR. I left or I right, it would be better to say. So till now we've introduced about 18 and maybe more and logics between F and WF. In this cube, these logics, of course I mean above 18 logic between WF and IPs and not between WF and F. And also if instead of D we put C, then we can get this cube. But the relation between the logics in the two cubes is mostly yet unclear. These four logics are the same, but these, of course this is also the same. But these four are not the same here. Consider that here I wrote C, but in this I wrote D. Generally, I can say that in these sessions, we introduce all logics that are between WF and IPC. These are sub-intuitionistic logics. This cube, in this cube, we cannot treat it with Kripke semantics, just we have neighborhood semantics for these logics. But for these logics, we have soundness and completeness with respect to Kripke semantics. And also this. Here C, here D. Okay. But what about the translation? I mean, I'm going to make a connection between the sub-intuitionistic logics and between the modal logics. In the last session, we say that, for example, modal companion of IPC is the S4, modal companion of the logic F is the K, and modal companion of the logic BPC is the K4 or BK4. And something like this. But now we're going to find the other modal companions of the some sub-intuitive logic that we have introduced today. Now we clarify the connection with modal logic, specifically with classical modal logic and monotone modal logic. Again, we consider the translation box from L, the language of propositional logic, to L box, the language of modal propositional logic. We translate the propositional letter P as P, this as conjunction of them, and also this. As incursive, of course, different from the usual box P that I explained it in the last session. And again, I'm going to say what is the modal companion, definition of modal companion. A logic L box is called a modal companion of logic L if for all A in L, if A be L probable, if and only if translation of A be L box probable. We know that E is the smallest classical modal logic with these rules, RE rule and modus ponens rule. And we know that the logic En is E plus box T, or instead of box T, we can write necessitation. I mean, this means that En, E plus box T is equal to X plus necessitation. These are equivalent. The proof of this also, for the proof of this also, you can refer to the book of Eric Packet, Modal Logic for Neighborhood Semantics. And also we know that the logic En is sound and strongly complete with respect to the n neighborhood frames for which for all W, W is a neighborhood of W. Then by this, and now that we can see that the modal neighborhood model for the logic WFN is exactly the same as the model for the logic En. So by this, we could prove that A probable in WFN if and only if translation of A be probable in En. So En is the modal companion of subintuitionistic logic WFN. But what about the more interesting monotone modal logics? We know that monotonic modal logic is the E plus this rule, A then B, box A then box B. We call it AM or M. Is the smallest monotonic modal logic, and it is complete with respect to n models with neighborhood closed under superset. I mean, if X is under neighborhood of W and X be under Y, then Y should be in neighborhood of W. And from the other side, we know that, and we prove that Vic Fn2 is sound and complete with respect to the n neighborhood models that has the superset condition. So these two logics, I mean WFN2 and M, has the same models, similar models. So we could prove that A is probable in WFN2 if and only if translation of A be probable in M. So we show that M, I mean monotone modal logic, is the modal companion of the subintuition logic WFN2. But also we know that the classical modal logic EC, that is E plus these axioms, box A and box B, then box A and B. And also we know that the logic EC is sound and strongly complete with respect to the class of neighborhood frames that are closed under intersection. That is, for all W, if XY in neighborhood of W, then intersection of them is also in neighborhood of W. For the proof of this theorem also, you can refer to the Packet book. And then also we have this theorem. This, of course, I didn't talk about this before, but now by the information that we have, we can say that the subintuition logic WFNC is sound and strongly complete with respect to the class of n neighborhood frames that are closed under intersection. So again, we can see that the neighborhood frame for EC and neighborhood frame for WFNC are similar. So we can think about the modal companion of WFNC. And so we could prove that A is probable in WFNC if and only if translation of E be probable in the logic ENC. ENC is the logic EC plus N. So the modal companion of the logic WFN is ENC. But we know that the smallest normal or Kripken modal logic K is equal to MNC. And we know that the logic K is sound and strongly complete with respect to the class of augmented neighborhood frames that is closed under superset and contains its core provided for all W in W. Intersection of all X in neighborhood of W should be in neighborhood of W. I said about this in the last sessions, in the first session. And also we know that the logic WFN2C is sound and strongly complete with respect to the class of n neighborhood frames that are closed under superset and intersection. Again, the frames of these logics and these logics in modal logic and this is in subintuitive logics are the same. So we can think about the modal companion. And again, we could prove that A is probable in WFN2C if and only if A be probable in K. Translation of A be probable in K. But because the modal companion, so this means that the modal companion of the subintuition logic WFN2C is the modal logic K. But before, in the last session, we proved that the modal companion of the logic F is also the logic K. So, because the modal companion of WFN2C and F are the same, we then immediately have that this corollary. I mean, the logic WFN2C equals the logic F. So till now, we could find modal companion in this cube. We introduced a modal companion of this, that is ENC, modal companion of this monotone, this is monotone, and the modal companion of this EN, and the modal companion of this. For these four logics, we could introduce modal companion of them. But what about these four logics? The slightly weaker, very natural logic WF has no standard modal logic companion. For WF and some of its extension, modal companion were studied with a binary modal operator. But due to the lack of time, I don't mention these, but you can refer to these two papers for the binary modal operator, and in that we introduce for all of them modal companions, of course binary modal companions, because when we don't have n in our logics, then that logic are not sound and we cannot prove sound and completeness of them to a neighborhood models. But since for modal logics, I mean non-classical modal, non-normal modal logics, we just have the normal neighborhood models, so their frames are not the same. The models are not the same, so we cannot talk about the unary modal operator, unary modal companions. So we should change our mind and think about binary modal operator, that you can see them in these two papers. But this last subject is about conservativity. First, the definition of conservativity. If L1 and L2 are logics with L2 extending L1, so L1 is under L2, and sigma is a class of formulas, then L2 is conservative over L1 with respect to sigma if all S in sigma, if L2 proof S, then L1 also proof S. This is the conservativity definition. Conservativity of IP, I'm going to give you a class of frames that IPC is conservative over WF on that class. There is a class of formulas with respect to which IPC and even CPC, I mean classical logic, is conservative over WF. First, we define this class, simple implication. A formula phi then psi is called a simple implication if phi and psi contains only conjunction and disjunction. We don't have any implication in phi and psi. Then we can prove that if IPC and even CPC proves a simple implication, then WF proves it as well. A difference arises between IPC and CPC when one introduces disjunction and conjunction of simple implication. The result still holds for IPC, but one has that WF just as IPC has the disjunction property and does not prove P then Q or Q then P, whereas CPC does. We know that this is true in CPC, but in IPC we don't have this. Of course, this theorem, it's obvious that this theorem also applies for the all stronger logics than WF. I mean for example, F, BPC, FT, and all of them. But now I'm going to introduce another class that IPC is conservative over F on that class. In order to show that, first we need to define the following class of formulas. A formula A then B with A and B containing only conjunction and disjunction, a simple implication. For example, this P or Q. This is the simple implication. Then a formula that is obtained by applying only conjunction and disjunction to simple implication is a basic formula. Applying the formula like this with only conjunction and disjunction, then we can get basic formula. And a formula like A then B with A and B basic formulas is a basic implication. Formulas, for example, like these. And also typical basic implication are the axioms C, D, and I that we introduced before. Then we could show that IPC is conservative over F with respect to simple implications and with respect to basic implication. And here again, the difference between IPC and CPC is essential because we know that in F we don't have Gödel-Dammet, we don't have these axioms, while this is true in IPC. Sorry, in CPC. Finally, we can state the following corollary. Assuming the rules of modus ponens, conjunction, and a fortiori, the system F is exactly the part of IPC axiomatized by each simple implication and basic implications. Why? Because we just need to check that all the axioms of F are simple implications or basic implications. And then we know that BPC is much stronger than IPC. BPC is much stronger than F. For example, we know that A then B then A and B is thrown in BPC. So I'm going to introduce another class that IPC is conservative over BPC with respect to that class. The smallest class satisfying the following clauses is called NNIL. 1. All proportional variables are in NNIL. If A then be in NNIL, then conjunction of them is also in NNIL. If A be in NNIL, then disjunction of them also be in NNIL. But if A in NNIL and B does not contain implication, then B then A also is in NNIL. We should consider that B does not contain implication. Then we can prove that IPC is conservative over BPC with respect to NNIL. So, finite model property, we could prove that WF is has the finite model property condition. I mean this definition. First, it would be better to give you this definition. We know that a model M is finite if and only if the set of words, it has the finite set of words. I mean W here should be finite. Logic L has the finite model property if and only if for all formulas A, if A does not prove by L, only if there is a finite model M for L such that M does not models A. Now we're going to show that WF has the finite model property. We're going to prove this result by means of finite theorems in so-called adequate sets. Step formulas phi is adequate if phi is closed under taking subformulas. For example, if A and B in phi, then also A should be in A and B also should be in phi, Step formulas delta is a theory in an adequate set phi if delta is under phi and for all A in phi, if delta proof A, then A should also be in delta. Then we could prove that this lemma, let phi be a finite adequate set and sigma be a set of formulas and D be a formula such that sigma union D is under phi and sigma doesn't prove D, then there is a consistent prime theory delta in phi such that sigma is under delta. Then we make the model like this, M phi, W phi, G, NB phi, V phi as follows. W phi has this condition, G or omniscient has these conditions, neighborhood also this, and valuation we define as this. It is easy to show that WF phi in W phi and that WF phi is an omniscient word, similar to the Kanikanda model that we had before, and we proved that. You can also check this. So M phi is in fact a neighborhood model. So we make a neighborhood model. Then we show that for every formula in a formula like E in phi, and for each gamma in M phi, we have this equation. E M phi is equal to this set. So finally, we could prove finite model property. I mean, if A is not proved from WF, then there exists a finite counter model for A. Though for the proof of this, we just need to consider the finite adequate set phi such that A is in phi and consider the model M phi. There exists a set delta then by the theorems that that in the previous slide we proved. There exists a set delta is under phi such that A is not in delta, and delta is node of M phi. Hence, M phi delta doesn't prove A, and so M phi is a finite neighborhood model which does not force A. So the proof is complete. So till now, we proved that W has finite model property. Also, we introduced some class that IPC are conservative over, for example, WF over F over BPC with respect to some special class. Also, we introduce some logics between IPC and F that we call them sub-intuitionistic logics. Some of them are complete with respect to neighborhood models. Some of them are complete with respect to Kripke models and neighborhood models, both of them. So thank you very much for your attention.